Okay, so we'll do brute force technique. For that, we'll look at string matching algorithms. So we are here given a string of length n characters, and then we want to search for a pattern of length m characters on this string. So, for example, if you're given something like nobody noticed him with all this blank spaces in between, and you want to search for a pattern, say NOT, what we would do is use this. Okay, so we'll compare this n with n, there's a match. So we'll then compare O with O, there's a match, but we'll compare then B with T, it doesn't match. Okay, so then we'll move on. So this is one block. Then move to the next block, NOT, compare N with O. Right there, we can say there's no match. This N with this O, right? It's no match. So you can move to this next block, NOT, compare N with B. It doesn't match. Move on. NOT, compare N with O. It doesn't match. We move on, right? So we move on until there is a match. So we have here NOT, N matches O, here's T is here. So you can return this index 7 where that's the first character where there is a complete match between the text pattern and the string. Okay. Now, so we do comparisons by block, right? So every block at most you will do, at the worst case, m comparisons, because like this we'll do all the 3 comparisons. And how many such blocks we will be doing? It is going to be n minus m plus 1. So for example, we have here n is 18, m is 3. The last block we'll do is this, right? 15. So which is going to be starting from 0. If you count, it's going to be 16 blocks. Okay, so 15 minus 0 plus 1, that's what it is. Okay, so n minus m plus 1 blocks, and in each block we'll do at the worst case m comparisons. So this is the number, this is the kind of formula you have to remember. Okay, at the worst case we have to do m comparisons in each block, and then n minus m plus 1 blocks. So we have some examples here. If you have 1000 zeros and you have a string like this, how many comparisons you would be doing? So you have again 1000 zeros, which is n is 1000, and m is 5 here, so n minus m plus 1000 minus 5 plus 1, which is 996, and here we have to compare, do all the 5 comparisons, right? Because there'll be match for the first 4 characters, only here there won't be a match. So it's going to be 996 times 5, which is 4980. Okay, now here there's going to be a match. Okay, there's not going to be a match right here for 1 0. So with just one comparison block per block we can find it's not going to match. So 996 times 1, that's going to be 996 comparisons. Then here there will be a success in the first comparison, but the second one will not match because we have all zeros here, right? So it's going to be 2 comparisons per block, so 996 times 2 is 1992 comparisons. Now we have this problem of trying to find the number of substrings within a string. The substrings starting with the characters A and ending with the character B. So given this complete string, so we do that by a linear scan of the string, and we maintain 2 variables, the number of A's that we have encountered so far and the number of desired substrings we have encountered so far. The number of desired substrings we have encountered so far is updated every time when you encounter character B. So the number of desired substrings is the number of A's we have encountered so far plus the number of desired substrings we have seen so far. Okay. So let's do this. So this is a given string and both are initialized to 0. Both are 0 because it's a D, so it's an A, so increment this to 1, but this is still 0. It's an A, increment this to 2, this is still a 0. So this is the same. Now a B, we increment, we don't increment A, but we increment this guy, which is basically this 2, and this 2 plus this 0. Okay, so that's 2. And then is an A, so increment by 1, so it's 3, and we just keep it as it is. It's a B, so we remind A remains as it is, but the number of substrings is whatever we have seen so far is 2 plus this number of A's we have seen so far 3, which is 2 plus 3, 5. Then A is incremented to 4, this is same as 5, same as it is. Now B is encountered, so A number of A's remain as it is, but the number of substrings we have encountered so far is 4 plus 5, 9, and then number of A's encountered so far is still 4, and then this is also same thing, 9. Okay, so with insertion sort, the way it works is we take up so if this is a sorted portion, okay, so if this is a sorted portion of the array from 0 to I minus 1, and we have this unsorted portion, let me go here itself. So we have this unsorted portion, so the first element in the unsorted portion will pick it up and try to insert it in the proper position in the sorted part of the array. So let's do this example first. So we have 45, 23 and so on. This is a given array. So to start with, this guy is sorted by itself, but we'll take up this 23 and see where we can insert the 23. So 23 of course is less than 45, so it has to be here. So now this is your sorted portion. Now we'll take up this 8 and see where can we insert here. So we'll compare 45 with 8, right? So we'll move 45, we'll make a copy of it basically, and then we'll compare 23 with 8. 23 is still greater than 8, so we'll make a copy of 23 here and we'll eventually insert 8 here. Okay. So now let's see 12. 45 is greater than 12, so we'll make a copy of 45 here. Then 23 greater than 12, so make a copy of 23 here. Then 8 is not greater than 12, so we'll insert 12 in 23's position because 23 has been moved to the right. Okay. Now let's do 90. 90 is not greater than 90 is greater than 45, so let's stay as it is. Now 21, 90 is greater than 21, so 90 cannot be here, it has to move to the right, so we make a copy of it and it's stored here. Then 45 is greater than also 21, so 45 cannot stay here, it has to move to the right, so we make a copy of 45 to the right, so that overrides 90. Then 23 is greater than 21, so again 23 cannot be there, it has to be moved to the right, so we make a copy of it and put it here. And then 12 is not greater than 21, so we insert 21 eventually in the position for 23. Okay, so the the best case for insertion sort is when the array is sorted as it is, because if the array is sorted as it is, say something like 10, 13 and so on, we don't need to make more than one comparison for each insertion, right? So it's sorted, so 10 is sorted by itself, then 13 has to be here, 17 has to be here, 19 has to be here. So just when you compare with the previous element, you will get to know that you cannot move the element anywhere, it has to be there as it is. So which means for every iteration we'll do only one comparison. So of the outer loop, every iteration is outer loop, phi equals 1 to n minus 1, we'll do only one iteration of the inner j loop. Okay, and this is a basic operation. You're checking whether you are moved to the left and whether there's nothing else to move to the left. Okay, of course you're comparing the values and see if the element in the current position has to be moved to the right or not. Okay. So for I equals 1 to n minus 1, we'll do only a comparison, one iteration of the j loop, so it is just 1. So it's n minus 1, upper limit minus lower limit plus 1, still n minus 1, so it's state of n. The worst case happens if you have to move entirely to the left and insert the element, and this happens if the array is reverse sorted. If the array is reverse sorted means if you have something like this, so you have to kind of move this element all the way to the right and do that many comparisons and then get something like this. Then again 5 has to be compared with 7, and then with this, and then eventually we'll move it to be something like this. Then 4 again has to be compared with each of this, and then only moves to the beginning of to the front of the first element in the array, right? So something like this. Okay, so the loop, the I loop runs from index I equals 1 to n minus 1, and j loop runs from I minus 1 to 0. So you can swap the limits, so it is j equals 0 to I minus 1, I equals 1 to n minus 1, so that's going to be I minus 1 minus 0 plus 1, that's simply I, so that's I equals 1 to n minus 1 I, so you can apply the limits as it is, it's n times n minus 1 over 2. Okay, because n minus 1 stands for n, then n minus 1 plus 1 is going to be simply n, so it is state of n squared. Okay. Now on average you do only half this comparisons, so j equals I minus 1 to I minus 1 over 2, 1 for the inner j loop, and then of course you can swap the limits, so it is j equals I minus 1 over 2 to I minus 1, I equals 1 to n minus 1, so that's going to be I minus 1 that's upper limit minus the lower limit, then plus 1, so it is I minus 1 over 2 plus 1, so that's going to be, now take an LCM, so it's I plus 1 over 2, taken this 1 over 2 outside, that's going to be it's an I plus 1 term, so you can say state of n square because it's limits from 1 to n minus 1, but we did solve it in class. So that's going to be, we put I equals 1 there, so it's going to be 2 plus 3 plus so on up to, if you put n minus 1, that is n minus 1 plus 1, right? So that's going to be 2 plus 3 plus so on plus n. So that's going to be, you have to add a 1 to it and then subtract it, 1 plus 2 plus 3 plus. So now this can be grouped as n times n plus 1 over 2 minus 1. If you take the LCM and all these things, this is going to be, you don't need to take all of this, you can just simply say the state of n square. Okay. Okay. So you need to be able to sort like this for insertion sort by working out the each iterations. You don't need to store the intermediate all these steps. For each iteration, just show one sequence where the element gets inserted in the proper position. Of course, for the time complexity, you have to show all the entire analysis, all the sequence of steps. Okay. Then divide and conquer. We have merge sort. So this should be familiar. So you're given the recurrence relation, I'll ask you explicitly to use master theorem. In that case, use master theorem. If I say use the induction approach or n equals 2 to the k approach, you have to use that approach. Okay, and sometimes I may say do not use master theorem, then you have to just solve by basic induction approach that we did in the first module. Okay, for the recurrence relations. So here you use master theorem. So a equals 4 here to start with this problem. Then b is 2, then n is 1 because it has to be theta of n raised to d, so d is 1, right? So a is 4, b is 2, d is 1, so b raised to d is 2 raised to 1 is 2, so a is greater than b raised to d, so the formula is d of n is theta of n log a to the base b. And a is 4, b is 2, so log 4 to the base 2 is theta of n square, log 4 to the base 2 is 2, right? Similarly, we'll do this. D is 2 here, so a is equal to b raised to d, so it is theta of n square, which is n to the d actually in general, n to the d log n, so this is n square log n. Then if you have 3, 2 raised to 3 is 2 cube 8, so a is going to be less than b raised to d, so t of n is theta of n to the d because the d term is dominating, so it's theta of n cubed. Then this is d is 0, so a is greater than b raised to d, so 2 raised to 0 is 1, right? So a is 2 is greater than 1, so a is greater than b raised to d, so it is theta of n log a to the base b. A is 2, b is 2, so it is theta of n log n raised to log 2 to the base 2 n, that's 1. This component is 1, so theta of n to the power 1, which is theta of n. Then a is 3 here, b is 3. This is n raised to 1 over 2, so d is 1 half. So b raised to d is 3 to the half, which is 1.732. So a is 3, b raised to d is 1.732. So a is greater than b raised to d. So it's going to be t of n is theta of n raised to log a to the base b. A is 3, b is b. So log 3 to the base 3 is 1. So theta of n. Now here we can say this is log n is going to be less than n to the 1 as n grows. So you can say our d, you can say this is theta of n raised to d where d is less than 1. So a is 4, b is 2, and d is less than 1. So b raised to d is 2 raised to something less than 1, which is going to be less than 2. So a is 4 and b raised to d is even less than 2. So a is going to be again greater than b raised to d. So it's t of n is n theta of n raised to log a to the base b, 4 to the base 2. So it's theta of n squared. Now in this case you can see a is 6, b is 3, and log n is less than n, right? So I can say again n square log n is going to be less than n squared times n cube. So n square log n is going to be less than n cube. Of course, n square log n is going to be greater than n squared. So we can say our d is between 2 and 3. So b raised to d is 3 raised to something 2 less than d less than 3. But of course then it's at least greater than 9, which is 3 square. So since a is just 6 and b raised to d is at least greater than 9, a is going to be less than b raised to d. So in that case the final answer is just theta of n raised to d, and we basically replaced n square log n with n raised to d. So the answer is theta of n square log n. Okay.